Okay, everybody, let's resume where we left off from the first video. I can only record 15 minutes at a time right now. I'll be trying to fix that limitation soon. So, all right, let's work on another problem formulation practice. And so please open your text to page 74. And again, there's going to be a problem like this. I remarked this earlier on test 2. So reading through that problem, I'm not going to recite it in detail, problem number 25 on page 74, but the gentleman's seeking to invest some money. He's got a variety of investment options. He's identified two primary options. There is a known projected set of returns on investment for each of the two options, and he's got some constraints he's identified. Said whatever portion he finally decides to commit, he wants to have 30% in a bond fund. He wants to mix it, allow him to have at least 7.5% total return. So Part A asks us, we're only going to work on Part A, to create a linear programming model that can use to determine the percentage to be allocated to each of the possible investment alternatives. So let's thinking about this. What's the objective? Is it a max or a min? I said earlier that we need to identify either a max or a min. Now, I'll give you that this problem doesn't clearly say that he's attempting to maximize his return, although he does imply that. He said he wants to get at least a total return of 7.5%, minimum 7.5%, but his objective would be to maximize his return. So let's go with max in this case. I will be very clear and explicit in other cases when I give you examples on a test. Item 2, step 2, define the decision variables. Well, we're being told that he's got two investment options for the money, a bond fund or a stock fund. Now, let's identify a variable character we can use for the decision options he's got. Let's let that equal the percentage of the fund monies that he's going to invest in a bond fund, B for bond. Let S equal the percentage that he's going to invest in a stock fund. Those are the two choices that we're given. Now we're told that the return on investments for bonds is 6% and for stock is 10%. So when we create our objective function here, again, we're always going to be a max or min. We can state this as we're attempting to maximize the right amount of return based on what percentage of monies we're going to invest here in the bond, what monies that we're going to invest in the stocks. We're going to get 6% on the bonds, that's what we're told, 10% rate of return on the stocks. Our objective function can be expressed as max 0.06b plus 0.10s. So that's our objective function. In many cases, when I give you problems to graphically solve, I will give you the objective functions. But in this case, we're going to be asking you to set things up because that's real world. You've got to be able to set these things up. Third step, let's describe and define each constraint. Now we're being told here that George wants to invest at least 30% of his funds in the bond fund. So we can express that to say that B, the percentage invested in the bond fund, must be equal to or greater than 0.3. All right. Second constraint he identifies is that he wants to have a total return of at least 7.5%. Well, given the fact that we're going to have 6% on the bond, 10% on the stock, it's got to be at least 7.5%, 0.075. Again, greater than or equal to, we can express that as. Lastly, this is something that's not utterly explicit in the language of the problem as defined, but I'm going to say that all funds must be invested, and that because he does say he wants to commit to the fund and so on, and so I'm going to say all funds must be invested. Therefore, the percentage must equal 1. You can't invest a fraction. Right? I hope this makes sense. Again, I've just walked you through two examples: the Par Inc. problem in the textbook, one of the problems from the text, problem number 25 in Chapter 2. And again, I will give you some more prep work next week so that you can be more comfortable in problem formulation, so that you can answer the one problem that's going to be like this on test 2. All right, let's go on to the second topic, graphical solution. and graphical solution procedure. Well, the text has a multi-page set of explanations to go along with this, starting at page 37 all the way over to page 47 or so, and it can be pretty complicated. I'm going to show you a similar way, slightly different. I'm going to walk you through it, and I want you to be able to do this when we have test number 2, because we're going to also have to do this in future tests as well. We get to test number 3, and even in one of the later tests, we're going to have to do some more graphing. So that's what we're going to be doing. We're going to be graphing or plotting the constraint equations. We're going to identify what feasible regions we have, and we're going to decide what the best expression is. So when we plot the feasible regions, we use this term extreme points. So I'm going to bring that up again, and I'll show you what that looks like. And the optimal solution to our types of problems are going to be found at one of these extreme points. So again, we'll have to only consider the extreme points of the feasible region. Now there are going to be at least 1, maybe 2 problems like this on test 2. So what does this look like when we graph things out? Let me first remark that you're going to want to have some graph paper or something that has some lines so that you can graph these out. And we're only going to stay in the plus value regions or quadrant of an XY graph. We're going to have 2 decision variables, therefore we have a horizontal axis and a vertical axis. We're not going to have a Z axis coming out at us in space in 3 dimensions because we only have 2 decision variables. Our decision variables would be typically X or Y, could be A or B, whatever they're identified as, could be B and S, but we'll plot one on the horizontal axis, another on the vertical axis. Typically, if we're doing X and Y, I'd like the X to be on the horizontal, Y to be on the vertical, A to be on the horizontal, B to be on the vertical is the way I'll do it. And when we plot the constraint variables, we will test what things to identify the feasible region. I'm going to show you how to do those tests. And once we identify the feasible region, we look for the extreme points, where the lines intersect with the axes, or where they intersect with each other. And in this case, there are 5 extreme points. The origin, this intersection, these 2 intersections of the 2 lines, and this intersection with the y-axis. So this is your instructions for the maximization process when we have a max problem. It's very, very similar for the min, but let's walk you through the max. So first, step number 1, formulate the model. It's often given to you. And again, I will, for the most part, when I'm doing the graphical solution or asking you to do it, I will give you the model. Step number 2, we're going to use an equality form to graph each constraint equation. What that means is that every constraint expression will typically be greater than or equal to or less than or equal to. Sometimes they'll be equal to, but we're going to treat them for the purposes of plotting as equal to. And then when we plot each of them, we'll identify the associated feasible region. So you may want to print this page for yourself, write it down, whatever it might be, because these are the steps we're going to follow. Step 3 is we identify the feasible region that satisfies all the extreme points simultaneously. All the constraints simultaneously. We'll label each extreme point, just as I showed you here, where we identified the extreme points. Fourth, we'll identify the decision variable values, for instance, the x and y coordinates at each extreme point. We may have to solve that using simultaneous equations. That might trip up some of you. It's the most difficult algebraic functions we're going to have to solve in this class. And lastly, we're going to evaluate or test the value of each extreme point to find the extreme point that has the best solution. For instance, in the max is the largest value, min is the smallest value. It is possible there's more than one optimal solution, although I won't put you in that kind of situation for a test. All right, so let's begin to walk through this with regard to the par inc problem again, and I'll start some steps and take you through it. All right, so referring to that par inc problem, we are given the mathematical model that we developed ourselves as well, but let's refer to that on page 36, and I'm going to write it again on the answer sheet that's coming up next. We know that we had 4 constraint expressions for the 4 manufacturing activities. And so we had the objective function, we had the decision variables, we had coefficients associated with those decision variables. So I'm going to show you how I used graph paper to do this, and I've got the handout answer sheet coming up next. All right, so the first step, writing down what we're given. Again, we solved this earlier when we did the problem formulation. Our objective function, max 10s plus 9d. The 10 is the coefficient value of the s decision variable. 9 is the coefficient value of the d or deluxe bag decision variable. 0.7 is the coefficient of the constraint associated with cutting and dyeing. I didn't write those down here. I've labeled these A, B, C, and D so that when I have them here plotted, you can see which line corresponds to which graph, which constraint. So when we come back to the steps, second step, use the equality form to graph and label each constraint expression. So step number 2, constraint A. Let's follow along here. If S equals 0, if we set S equal to 0, D will be equal to, the equality, D will be equal to 630. If D is set to 0, then S will be equal to what? 630, then you'd have to bring this over, divide by 0.7, bring it over to this side, divide on this side, S would be equal to 630 divided by 0.7, that would be 900. Now, what we want to do is plot this particular line, this particular constraint, and that constraint is represented here, and where we have 900 is here for the where S equals 900. Remember, I put S here, D here. You could have done it the other way, but I've done it this way. Standard in the x-axis, deluxe in the y-axis. So I plotted this point here. S is equal to 900. I put a value here for D. D equals 630. I connected those 2 points, and then I decided which direction does my feasible region go for this particular plot. So what we want to do in this case is look at a value of S and D in this area versus something in this area. So let's pick a point down here toward the origin where S is equal to 100 and D is also equal to 100. Pick that point. Decide whether or not the feasible region will be in this direction or will be out in this direction. If we say S and D are each equal to 100, and we look at that constraint, 100 times 0.7 is 70, plus D, if that's equal to 100, that would be 70 plus 100. Is that less than or equal to 630? Check. Yes, it is. That tells us that the feasible region for that constraint lies in this direction toward the origin. Now, we're going to plot the other 3 constraints. I label them B, C, and D. We do the same thing, if setting the S, the variable, equal to 0 and seeing what D results in, setting D equal to 0, and then determining the value of S. We plot each of those points, and similarly, we have plots B, plot C, plot D. And for each of those plots, we do the same thing with regard to the feasible region. In every case, each of those 4 cases, the feasible region is toward the origin. Since the feasible region for every one of those is toward the origin, the net feasible region for every one of these is this area here that I am triangulating, sort of triangulating. It's not a perfect triangle, but it begins at the origin, goes up to that point, this point, this point, and this point. That means that there are actually 4 extreme points. I'm not going to count the origin as an extreme point in this case, because the origin at a value of S and D both equal to 0 is not going to pan out for a max value. That would simply be 0. So I've labeled these points 1, 2, 3, and 4. And similarly, I've set up a table over here for those points and what the values of S and D are at each of those. Now I'm running out of time. I'm going to have to make another recording for 15 minutes. I'm going to come back to this in part 3.